Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to the online data structure class. What we will be doing today is to start the fourth online lecture on chapter 5, which is on hashing. Today's topic will mainly focus on resolving secondary clustering caused by quadratic probing, which is one of the collision resolution methods. Although primary clustering caused by linear probing can be avoided by using quadratic probing, however, if multiple keys hash to the same bin, the same probing sequence of numbers will be followed for all the keys. Secondary clustering may be a problem if the hash function does not produce an even distribution of entries into the hash table. If you have some size of your hash table M, if you are hashing key values, a sequence of outputs from the hash function must appear to distribute these values evenly across the bins. Basically, all bins are expected to contain roughly equal number of hash values. Now, there exists techniques that eliminate secondary clustering, and the one that is most popular is double hashing. Double hashing will associate with each element an initial bin defined by the first hash function and a skip defined by the second hash function. Important aspect of the second hash function is that it should never evaluate to 0, and it must make sure that all cells can be probed. Basically, double hashing uses the idea of applying a second hash function to the key when a collision occurs. The result of the second hash function will be the number of positions from the point of collision to insert. Choosing the jump value with a different hash function, that is f of I with input I equals I times second hash function for input key. A popular second hash function for input key equals R minus key mod R, where R is a prime number that is smaller than the size of the table, will often work well. The overall expression for double hashing function will be as follows: h to base d function input key and integer I equals your hash function plus variable I times your second hash function. Here h of d is the abbreviation for your double hash function. H is your hash function, h to input key is the hash value of the input key, h to base 2 is your second hash function, h base 2 input key. You can term this as second hash value of the input key. Variable I is your probing sequence, which will be for I equals to 0, double hash function equals to hash function h of input k. For variable I equals to 1 equals to hash function plus second hash function. For variable I equals to 2 equals to hash function plus 2 times the second hash function. And similarly, for variable I equals to 3, double hash function equals to hash function plus 3 times the second hash function, and so on. Here m is prime number and second hash function equals r minus k mod r, where r is a prime number smaller than table size m. Example, if m equals to 37, we may pick r equals 23 or even r equals 11, as long as it's a prime number, and it should be less than table size m. The choice of prime number is important. If it is not a prime number, we may run out of alternate bins very fast. If m and r are relatively prime, we'll end up probing the entire table successfully. Now, performance-wise, double hashing collision resolution technique is much better than linear or quadratic probing. Does not suffer from clustering, but computational wise it's more expensive since it requires computation of a second hash function. Let's consider an example. The hash table size m equals 10. Please note that we have not picked a prime number for the table size. This is just for demonstration. We will be inserting the following keys in sequence: 89, 18, 49, 58, and 69. The hash function h of key equals key mod 10. The second hash function equals 7 minus key mod 7. Please note here that r equals to 7, and this we have picked a prime number. Let's insert 89 in our hash table by using double hashing technique. H of base d for input key equals 89 and probing sequence variable I equals to 0, which equals 89 mod 10, and that equals to 9. Therefore, we insert number 89 into bin 9 of our hash table. Now let's insert number 18 into our hash table. The hash value computed for 18 by using double hashing variable sequence of probing I equals to 0 is 8. Therefore, we insert number 18 into bin 8 of the hash table. Now let's insert number 49 in our hash table. The hash value computed for number 49 by using double hashing when sequence probing variable I equals to 0 is 9. But bin 9 is already occupied by number 89, and thus which causes a collision. We further increment the double hashing function variable I to 1 and compute the hash value, which now equals 16. We apply wraparound in order to insert 16 into our hash table. Once we reach bin 9, then we wrap around to index 0 index 0 is counted as index 10. Similarly, index 1 is counted as index 11. Going ahead in similar fashion, index 6 is counted as index 16. Thus, we insert the number 49 into index 6 of our hash table. Now let's insert number 58 into our hash table. The hash value computed for 58 by using double hashing when variable sequence probing I equals to 0 equals 8. Now bin 8 is already occupied by number 18, which causes a collision. We further increment the double hashing function variable I to 1 and compute the hash value, which now equals 13. We apply wraparound. Once we reach bin 9, then we wrap around to index 0. Index 0 is counted as index 10. Going ahead in similar fashion, index 3 is counted as index 13. Thus, we insert the number 58 into index 3 of our hash table. Now let's insert number 69 into our hash table. The hash value computed for number 69 by using double hashing when variable for sequence probing I equals to 0 is 9. But bin 9 is already occupied by number 89, thus which causes a collision. We further increment the double hashing function variable I to 1 and compute the hash value, which equals 10. We apply wraparound again. Once we reach bin 9, then we wrap around to index 0. Index 0 is counted as index 10. Thus we insert the number 69 into index 0 of our hash table. Here is a pictorial representation of three probing sequences, which are linear probing, quadratic probing, and double hashing, trying to resolve collision. The linear probing sequence is checking for an empty cell by incrementing the sequence linearly one by one until an empty bin is reached. As seen in the picture, the linear probing is trying to search for an empty slot by trying at index I plus 1, which is the first try, then increment the sequence again by 1 and does a second try, further incrementing the sequence by 1 and does a third try, and so on. The quadratic probing sequence is to check for empty cell by adding successive values of an arbitrary quadratic polynomial, and in our case that polynomial is I square. As seen in the picture, the quadratic probing is trying to search for an empty slot by trying at index I plus 1, which is the first try, then it increments the sequence by 2 square and does a second try, further incrementing the sequence by 3 square and does a third try, and so on. The double hashing function checks for empty cells by adding values of second hash function as well with the first primary hash value. Although the primary and secondary hash functions are not defined here, but its principle of working can be observed pictorially, where in order to find an empty cell, it attempts first, let's say at index I plus 5, which is the first try, and then the second try, it does it at index I plus 4, then the third try, it does it at index I plus 8, and so on. You can observe double hashing technique toggling between first higher and then lower indices in order to find an empty cell such that collision can be resolved. Double hashing has performance that is almost optimal. However, calculating the second hash function does provide some additional computational inefficiency. Double hashing has poor memory performance but exhibits virtually no clustering. Linear probing has the best memory performance, but it's most sensitive to clustering. Quadratic probing falls in between linear probing and double hashing. Now let's cover the last topic of chapter 5, which will be now rehashing. If the hash table becomes too full, the running time for operations will start taking too long. In other words, its performance falls. The time complexity order 1 property for inserts, search, and deletes for hashing will be lost. We anticipate that probe collisions will become higher as well. What solution can we apply? One of the solutions that can be applied is to build a bigger hash table, approximately twice the size of the original, and rehash the keys of the old hash table with a new associated hash function. Basically, scan down the entire original hash table, compute new hash values for each element, and then insert it into the new table. Practically, we rehash when the table is half full, when an insertion fails, or even when a certain load factor has been reached. For separate chaining, the load factor between 1 and 3 is a good time to resize. For open addressing, load factor between 0.5 and 1 is a good time to resize. Please note that rehashing can be applied individually, standalone, and it can be applied across collision handling schemes as well. Now let's take an example. Hash table size equals 7. We will insert the elements 13, 15, 24, and 6 in this sequence. The hash function equals key mod 7. We will use linear probing to resolve collisions. So far we have hashed all the numbers into hash table. Our load factor, which is number of elements inserted divided by the table size, equals 4 divided by 7, which comes out to 0.57 right now. So let's insert 23 now. Once inserted, the load factor equals 5 divided by 7, which equals 0.71. Because this table is too full, we need to enlarge it. And let's pick size 17 and redefine the hash function. Further to the example, here the hash table size equals 17. The hash function equals key mod 17. The old table is scanned and the elements, which are 6, 15, 23, 24, and 13, are inserted into the new table in the same sequence. Then we use linear probing to resolve the collisions. Now, the load factor, which in this case the number of elements inserted divided by the table size, equals 5 divided by 17, comes out to 0.29. The time order complexity for rehashing. It takes order n time to rehash since there are n number of elements. We should rehash at n by 2 insertion. Basically, when the load factor is 0.5. The order n time cost for rehashing can be treated as constant additional time per insertion into the new hash table. Now for the summary of hashing. Hash tables can be used to implement insert, search, and delete operations in constant average time. Now, for these time bounds to be valid, special attention has to be paid to the load factor. For separate chaining hashing, your load factor lambda should be close to 1. For open addressing hashing, lambda should not exceed 0.5. If linear probing is used, performance degenerates rapidly and the load factor approaches to 1. Rehashing can be implemented to allow the table to grow, thus maintaining a reasonable load factor lambda. For homework, here's an example taken from another textbook which states to perform the operations given below in the given order on an initially empty hash table of size 10 using linear probing with I equals to 1 and the hash function which equals key mod 10. So basically you have these operations: insert 18, insert 26, insert 35, and so on. So the required probe sequence, since it's linear probing, will be then your hash value plus I and the whole term mod 10. So where I is equals to 1. So you can see this table which shows the result of the above operations. Go through this example. On the next slide, it further continues. For homework, I would like you to repeat this example by again using linear probing, but this time use the hash table size 11. That's basically one part of the homework. Now the second part, part B, do the above example by quadratic probing. Same type of table I would like to see with same operation, probe sequence and result, but needs to be done by quadratic probing and use hash table size 11. So for your C part, do the above example again by implying double hashing. Same follow-up with the result tables. Use primary table size 11 and you can use the secondary one R equals to 7. So that's part C. Then your part D, I would like you to do the example by using rehashing, and this time use table size 23 and do all the operations that are listed in this example.